This is the AP Calc AB 2019 FRQ problem number 2. It says that the velocity of a particle p moving along the x-axis is given by the differentiable function v sub p, where v sub p of t is measured in meters per hour and t is measured in hours. Selected values of v sub p of t are shown in the table above. Particle p is at the origin at time t equals 0. They give us, therefore, this last sentence is the initial position of the particle. We don't have a function for particle p's velocity, but we do have 5 instantaneous velocities at 5 selected points in time over the interval 0 to 4. And question A is asking us to justify why there must be at least one time t in the interval 0.3 to 2.8 hours at which v sub p prime of t, which is the acceleration of particle p, equals 0 meters per hour. This problem has all to do with the mean value theorem. The mean value theorem tells us that if I have a function that is continuous over the closed interval and differentiable at all of the interior points over the interval, it means that for any interval, there is at least one point in the interval where the instantaneous rate of change will equal to the average rate of change over that interval. Well, applied to this problem, since we're talking about the interval from 0.3 to 2.8, we're talking about the velocity at 0.3 hours, the velocity at 2.8 hours. Both velocities are 55. So if I were to calculate the average rate of change of the velocity, which I'm going to call acceleration, right? Because the average rate of change of velocity would be average acceleration, right? The acceleration would be equal to 55 minus 55, right? 55 meters per hour minus 55 meters per hour divided by 2.8 hours minus 0.3 hours. That obviously is 0, right? So 0 meters per hour or meters per hour squared. So that's the average acceleration. That tells me then there's at least one point in time in between 0.3 and 2.8 where the instantaneous acceleration is 0 meters per hour. So this is what an answer might look like written out completely. The average rate of change of velocity in the interval from 0.3 to 2.8 hours is 0. And given that v sub p of t is continuous and differentiable, by the mean value theorem, there must be at least one point in time between 0.3 and 2.8 hours when the instantaneous acceleration v prime sub p of t is 0. That was part A. Let's move on to part B. Part B is asking us to use a trapezoidal sum with the 3 subintervals that are given to approximate the value of 0, the integral from 0 to 2.8 of v sub p of t dt. All right, so we're trying to estimate this integral. So I'm going to write this integral that they're asking us to estimate. And I'm going to say that it is approximately equal to. Now, I am going to use a trapezoidal sum, which means that the first trapezoid is going to be involving these numbers here. These right here, the 0 and the 55, these would represent the lengths of the bases of the trapezoid, because these trapezoids are sideways on the velocity versus time graph. So I'm going to take the area of the first trapezoid, and I'm going to take the average of the 2 bases of the trapezoid, so that's 55 plus 0 divided by 2, and I'm going to multiply that by the height of the trapezoid. The height of the trapezoid, of the sideways trapezoid, is the difference in the time along the time axis. So we'll say it's 0.3 minus 0. All right, now moving on to the next trapezoid. The next trapezoid is going to be this one. So the heights, the lengths of the bases are going to be 55 and a negative 29, and I'm going to average those, divide by 2, and then I'm going to subtract the two time values. That gives me the height of the trapezoid. All right, then the last trapezoid is going to be the one that involves these sections here. And so that's going to be negative 29 plus 55. Those are the bases of this trapezoid. I take the average and then take 2.8 minus 1.7. If I run those out on my calculator, which I'm not going to do here on the video, you will get 40.75 meters. Okay, it doesn't ask us to give an explanation. It just tells us to find the sum, and we have done that. There is our final answer there. All right, let's move on to C. Part C says a second particle Q also moves along the x-axis, so that its velocity over this interval 0 to 4 is given by v sub q of t, 45 square root of t times cosine of 0.063 t squared, and that's meters per hour. Find the time interval during which the velocity of particle Q is at least 60 meters per hour. Find the distance traveled by particle Q during the interval when the velocity of particle Q is at least 60 meters per hour. Well, we're going to be using our calculator on this. This is a calculator problem. Now, what I'm going to do here on the calculator, I've already entered in the function v sub q of t. So this is the velocity function for particle Q. And let's just scroll across and make sure we have it entered in correctly. Of course, it's in x rather than t, but that's okay because that's what my calculator uses for the independent variable. Now, the best way to do this graphically is I'm also going to plot a horizontal line 60 to represent 60 meters per hour. So in Y2 I have 60. I'm going to go into my window. I'm going to set my window for the x values or t values to go from negative 0.1 out to 4.5. I put negative 0.1 so I can make sure that I see the y-axis, and I go out a little bit beyond my interval out to 4.5. My y's, I'm going to go from negative 10 to 75, and then I'm going to graph these two functions, and that's what I get when I graph them. So you can see my velocity function is here, and here is my velocity of 60. So what I want to do is find out what these points of intersection are, because this section here of the graph that's above 60, that's when the particle Q is going obviously more than 60 miles per hour. So we'll find out what those are by doing second function calc. We're going to say intersect. There's the first curve, there's the second curve. Hit enter again. It shows me that at x equals 1.8662 I have that's one of the boundaries when it first reaches 60 meters per hour. Finding the other intersection point, let's do that. So we'll do second function calc, intersect. There's my first curve, there's my second curve. I'm going to move it a little bit closer so it picks up that point. And that's at 3.519. So the interval over which the particle is going at least 60 meters per hour is the interval from 1.866 to 3.519 hours. Okay, so we'll write that out as an answer for the grader. So we'll say that 1.866 to 3.519 is the interval over which Q is traveling at least 60 meters per hour. Now it also wants me to find the distance traveled by particle Q during the interval when it's at least 60 meters per hour. So what I'm going to do is I'm going to have to integrate, right? If I want to know distance and I have a velocity function, the distance is going to be the integral between 1.866 and 3.519, and I have to do that by taking the absolute value of the velocity function, right? Because distance means I want to know how far in absolute terms the particle traveled without regard to direction. So I always want my summations to be positive. So I'm going to do that integral. I'm going to use my calculator to do it. So I'll pull my calculator over. We'll go back to the main screen. We'll do we're going to do math number 9. We're going to integrate from 1.866 up to 3.519. We're going to do the absolute value. So we'll take the absolute value. We're going to do alpha F4 so we can tell it to use Y1. And we'll put in our X here and we'll integrate. And we get 106.109. All right, so that is the distance. So we can say that this is equal to 106.109, and this is going to be in units of meters. Okay, so we are now done with part C. Let's move over to D. And it says at time t equals 0, particle Q is at position x equals -90. Using the result from part B and function v sub q from part C, approximate the distance between particles P and Q at time t equals 2.8. So it's quite obvious I need to get the position of the particles both at 2.8 and then subtract their positions. So let's start with the position of particle Q. So I'm going to say x sub q of 2.8. So in other words, the position at time equals 2.8 hours would be whatever its initial value was at t equals 0 plus the integral from 0 to 2.8 of v of q, v sub q of t dt. So now notice I don't have an absolute value on this because I actually need to find the position, which means I have to consider displacement, not distance. So I'm going to come up here and edit this and get rid of the absolute value here and just do y1. And we are going to go from, we're going to change our limits here. We're going to go from 0 to 2.8. And this is for particle Q. And when I execute that, let's see what we get. 135.938. So what we're going to say is, okay, my initial position they told me was -90. So I've got -90, and then I have a displacement of 135.938 between 0 to 2.8. That ends up being a final position of 45.938 meters. I now have to find the position of particle P at 2.8. That also is going to be oh, and this should be a Q up here. So this should be x sub q. All right, this would be xp of 0 here. And I already determined what the position was in B, because basically I would be integrating 2.8 of v sub p of t dt, but we estimated that, right? We got this integral through an estimation using the trapezoidal sum. So this ends up being 0 plus 40.75. That was our estimate. And we were told also in the problem that the initial position of particle P was 0. And so we've got 40.75. Okay, so if I subtract those two values, I get 5.188 meters. So my final answer is the distance between particles is, we'll say particles P and Q is 5.188 meters with particle Q being further to the right because it's got a higher position, 45.938. Okay, that concludes the 2019 FRQ number 2 for AP Calc AB. Hope you enjoyed the video. If you have any comments, leave them here. Thank you very much.